Hi everyone, and welcome back. In this video, in the past two videos, we've been taking a look at what neural networks are in general, or at least like the four neural networks, how they process data. They start with some input features and then go all through the forward pass and basically can create any like output you want with respect to the dimension and also like the numerical range of the output. But in this video, we would like to take a look at like the common tasks that you may want to tackle with a neural network, especially if you have like a supervised learning task, meaning usually you have one target variable of interest. And the common target variable that we usually observe in such tasks are either a real-valued number. This is what I refer to as the regression task or regression problem. And then classification. And with respect to the modeling, classification is often distinguished between a binary target variable, that means you have a yes or no variable, or a variable that has more than two categories, right? So now let's take a look and continue in the notebook from the past videos. And here you can see that I'm going to run through all these three different tasks. We're going to see at some point that things are to a certain extent very similar, and you only have to modify a few minor parts of the overall process to specialize the way what you're doing here for the task that is going to be solved. For every example, I am simulating data here, so there's no real data. However, it's quite nice that we, for instance, by the sklearn package, we have it can be easily done to create reasonable data. Reasonable in terms of that it's not too simple. The relationship between the target variable and the feature variables is not too simple. And we have like freedom in terms of how large we want to have the data set to be created, and also up to a certain extent, so how many feature variables we want to have. So here I use the make Friedman function. If you are interested how that exactly looks like or how it's generating the data, just Google for it, and in the sklearn documentation you can find the functional relationship that is used to simulate data. You will find out that this is basically not like strictly like a linear regression model with respect to the data generating process. So it already includes some interactions and some nonlinear relationships, which is where neural networks can shine because they are more or less very good function approximators. So here I'm simulating 2000 observations. We have 5 features, and this is what is called a pairs plot. So basically you can see on the diagonal line here the histograms for the unique variable. So here we have x1, x2, x3, x4, x5. We can see by this means that this seems to be all a uniformly distributed variable here. Okay, right? So it's seems to be in the numerical range between 0 and 1, and more or less has very similar frequencies regarding like in the where exactly the realizations can be observed. And here, and I think this is the most important row, then we can see the pairwise relationships between x1 and the target variable y, x2, x3, x4, x5, and also the distribution of y. This y seems to be, at least by a graphical inspection, more or less similar to a normal distribution, or at least it is symmetric distribution. And we can see here that to few, at least on a pairwise level, some variables, for instance here x4, x5, they seem to have a rather simpler relationship to the target variable, so more or less like a linear relationship. You can imagine here a straight line going through that, but also, for instance, some non-linear relationships. So I think this is strongest or the best. We can see this is for x3. We can see this is more or less like a U-shaped or relationship. And this is exactly where neural networks tend to be better than simpler models such as a linear regression model, because a relationship like this can never be captured by a linear regression model. And also what we do not see here, but what I know from the data simulating process, is that you only are able to capture interactions. So for instance, an additional impact of x1 and x2 on the target variable you can only include this in a linear regression model if you know about it or if you're interested about it and specifically introduce that in the model equation. However, neural networks also, the way how neurons are generated, are able to capture interactions and to detect them by themselves. You don't need to specifically define them in the model, because if you, like, for instance, have like a neuron, or like, if a neuron is created, for instance, by giving specifically a large weight on x1 and x2 in the input layer, this neuron may representing an interaction effect between x1 and x2, right? But this is really detailed, but maybe just to give an impression about the data here. And then in this videos, I'm more like now at the pragmatic level. So how would you exactly do this? How would you train a model here? Let's zoom in a little bit. So the first step, and never forget it, because if you forget, you're likely going to realize it because it doesn't work. However, if you start with this, always remember, first step when you want to train and fit a neural network to data is to normalize at least the input features. Otherwise, you're very likely to run into numerical problems for the optimization process. And here there are different choices that you can make. I'm choosing here what is called the min-max standardization. Also a very common one, obviously, is the standardization by the mean and the standard deviation by itself. So if you do it like this here, what will result is a normalized variable of the input that has that is put between that is within a user-defined numerical range. So the first step is to bring this in the range between 0 and 1. This is done by this here. And then if you want to, and this is, I would say, also very common, you can now extend this numerical range arbitrary as you want to. For instance, between -1 and 1, then you would set xu to 1, which stands for x upper, and xl to -1, which stands for x lower. And so what result here, if you do this for every feature variable, is that every feature now is in a comparable numerical range. And specifically here, for instance, if I set the numerical range between -1 and 1, now every input feature is between -1 and 1. So this is what you can see here. We've seen in the beginning. So this is how the first 5 observations, so the first 5 rows look like here for x1, x2, x3, x4, x5. We've seen already in the pairs plot that they are originally between 0 and 1. So to be honest, here it would not strictly be necessary to normalize the data, but anyway we do it because even this helps here, what I'm doing here. And I think it's more like generally you would never ever get already feature variables that are normalized to a certain extent, so you should get used to that right from the start. So, but what we see here now, this is then the standardized version of, for instance, this observation. And all these standardized versions here, they are like every column here is between -1 and 1. All right, when we want to train a regression model, this is not really necessary specifically, but especially for PyTorch, I would say this is very makes life easier a lot. So the first thing what we always want to do is to split our overall data set into at least training and test data, right? The background information here is, or the reasoning is, that as neural networks are really flexible and capable of capturing arbitrary relationships, they are also likely to overfit. Loosely speaking, that means your model is going to make very good predictions for the data it observes during the training process. However, it will fail to do equally good predictions for new and unseen data because it has been trained too specifically on the training data. And this is not what we want, because obviously we train a model to make predictions for new and unseen data in the future. And these predictions should be as good as during the training process. And more generally speaking, if this is true, then we also kind of can assume that the neural network really identified more or less like a general relationship between the feature variables and the target variable, right? So this is why we at least split the data into two data frames, which are usually referred to as training and test data. Obviously, you can become more sophisticated here and do cross-validation and so on, but this is not what this video is about, so we just ignore it for a second. And then what is really helpful here, like first of all, we split the features as well as the target variable, and we create what is called a tensor data set and build on that a data loader. And that is because usually when we do this, gradient-based iterative learning for neural networks that we've been talking about, we not do this on the full data sample, and we also usually don't do this on a single observation itself. We do this on what is called a batch of the original data, right? So just to repeat this shortly, so when we train a neural network, kind of see it here somewhere above in the script, what we always kind of do is we have some parameters, and during training we take a look at what is the loss value. The loss value is more or less like a feedback function. That is, the higher the worse the predictions are. And then the gradient are the partial derivatives. So how much is, or in which direction is the loss value going to change if I increase that specific parameter by a very small unit. And if it is positive, that means further increasing the parameter would increase the loss. So if that's the case, if we have a positive sign here, we want to reduce the parameter. This is what would happen here. So this is the old parameter. Then we have here just the learning rate, usually a small number. Don't ignore it for a second. And we have here a positive value. That means if that is positive, what we're going to do is we're going to subtract something from our current parameter. So that is going to reduce the parameter. And this is exactly what we want, because the gradient tells us if you would increase it, it will increase the loss, and we want to reduce it, so we decrease it. And it's completely the other way around. You can do it for yourself if you have a negative sign for the gradient. And this is how we iteratively train the model. And we do this here by showing for each of those gradient iteration steps the model an example of, for instance, here 16 observations at the same time. I set this here to 16 because then this is how you can picture what it looks like, what the model observes when it does the gradient iteration for one single step, right? So it gets 16 examples of observations from the data set. Here, the first one for the feature variables, and here the corresponding target variable. And then we, initialize and define a neural network. And in the first step, we use then this network to make the predictions for those 16 observations. So let me execute this, that we have it in the memory space here. So let's go through those steps. And then what we would do here is we define a neural network, and we can create predictions for those 16 observations very quickly. But also, this is not what I want to talk about this in full detail, even if you take a look at how this is done with pytorch. But I think this is very well documented at the pytorch site itself. So whenever we define a neural network here, we use the parent class of the neural network module class from pytorch. And usually when we initialize the model, we need to define the layers that we're going to make use of, as well as the activation functions when we do the forward pass through the network. So the linear layer, what it always does is just the simple matrix operation. So you have input features times weight matrix plus bias. And activation here is the ReLU function. So again, it's like the maximum of the value itself or 0. So basically it keeps the positive numbers here. And then here the forward pass. So first for our input x, okay, so in that case here, that would be those observations for the first batch here. So that what we do here is we calculate x times the weights plus the bias, and then activate it with the ReLU function. This creates a layer of hidden neurons with the hidden dimension size here. And then these hidden neurons are one more time run through the affine transformation. So meaning a second layer with different weights and a different bias value, but it's just the hidden neurons times a weight matrix plus the bias. And the output dimension here is then set to 1 in that example, because we have only for every observation one target observation that we're going to want to compare, like the prediction of the network to the target observation here. If you want to train a model, we need to define the model. We need to define a loss function here. As this is a regression task, we're going to use the squared, like the deviation between predictions and observations to the power of 2. And here defining an optimizer means basically to set the rule for the gradient update. So the SGD is really what we've been looking above. So it's just like calculate, so it stands for stochastic gradient descent. And this is take a batch of the data, calculate the gradient with respect to that data, and then apply the gradient update rule as defined above. So here just for one example of the data, so this is where these are X and these are Y values. Then this is just, to make sure that we're starting with a new gradient information here. We create the output, we calculate the loss, and loss backwards basically automatically calculates the gradients here. Okay, so you can take a look inside if we execute this. So this is how the model parameters look like in the beginning. Here they have been like randomly initialized. Okay, so we have 5 feature variables in the beginning, and here we define that the model is supposed to generate 3 hidden neurons. So we have a 3 times and that's, so we need to make sure that we have a 5 times 3 matrix. Here this is the transposed version, so this is a 3 times 5 matrix for the weights of the first layer, and then we add to every hidden neuron 1 bias. So this is why we have those 3 values here. And then out of those 3, we create 1. So we have a 3 times 1 here and 1 bias for the second layer. Okay, so those would be the parameters. Then if we calculate now the gradient, so for the first predictions, so basically you can also take a look here if you're interested. So the outputs would be the predictions currently of the model, and the targets would be the observations for this dataset. As you can see, they are far away because we, as I said, initialized the model with random parameters. So obviously at this moment in time, it is not very good. And then we, calculate the loss function and calculate the derivatives. So I think here they are already have been calculated. So for instance, for the first parameter, this information would tell us if you would increase this parameter, it's going to reduce the loss function. So that is a good thing. So that means the first parameter here, which is currently around 0.3, is going to be increased a little if we do the gradient update step. This is exactly what you can see here. So if you do optimizer step, then this step is conducted. And then take a look at the parameter afterwards. So here it's very small to see, but it is a slight increase. So here we have 2.988 something, and after the increase we have 2.99 something, right? So this is very small, but small is a good thing here because we slowly and gradually want to improve the model here. And also this is controlled by the learning rate. So here in the optimizer, we have set this to 0.01. So that means only the 0.01 times the current gradient is added or subtracted to the current parameter here. And now we're going to do this not only for the first 16 observations. We again collect again and again 16 observations from the dataset and conduct this optimization or this update steps. And once we are done through the overall number of observations of the data sample, this is what is usually referred to as an epoch. And again, this then can be done for multiple times here. Okay, so this is what you then see here in a loop. So in the beginning, it's just definition. Okay, so the model is defined. We set this to training mode. We define a loss function, and here we define an optimizer. Here I already use Adam, which is a slightly more sophisticated version on the way to update, to conduct the gradient update. Still, the original idea stays the same. Then first, let's take a look in the inner loop here. So for an epoch, what we do here is we iterate through the data sample and exactly do all those steps that we've been taking a look at, like above. And then for every batch, we can calculate the current loss. And after once we are done through all the batches of the data sample, we can calculate the average loss for the training data. And here, when we set this to torch no grad, that means we now just using the model without the gradient information and without updating the parameters. So this is what we, even during training, we can take a look at the loss for the test data. But, and this is important, the information of the test data is not used in any way to improve or update the model. And this can not only be done, this can be done multiple times. So if we do this, then this is how the training process looks like. For you, important to understand is an epoch is really now going through the whole data sample once in batches of, here I think we still have a batch size of 16. You can see, for instance, this is for the training and test loss for the first epoch. And for instance, here, if you compare the numbers, it really quickly is reduced after, for instance, 10 epochs, but still, and then you can also see that the greatest reduction already here occurs within the first 5 epochs here. And what's also important here to see is that the loss of the training and this test data seems to be comparable at this all the time. This is a good thing because it gives us an indication of overfitting here. Okay, so this is the progress of the training loss and the test loss. And once we're done with the model, we of course can, this is done by this here, make predictions for the overall data set for training and for test data with the now model with frozen parameters. And if you want to, you can evaluate, of course, now again, the model. So for instance, one thing which I consider to be reasonable is a visual inspection. So here we plot the predictions versus the actualizations. A perfect model would, create all points here on a diagonal line here. But if like the points here are more or less like going around a, diagonal line that we might have in mind here, I would say still this is a good, more or less seems to be reasonable here, because usually your model should or is not able to fully create perfect predictions all the time. For instance, what would mean that point here? So the prediction is close to 15 and actualization is 7. So everything that is below the diagonal line is like more or less your model over predicting. Everything above is more is a little of underestimation here. But still, I would say this seems like to be quite a reasonable model already. And then last but not least, you can also use a scoring function. Here I'm using the R2 score, which basically compares the performance of your model to a naive prediction, meaning how much do I improve once I include the information of the feature variables with the trained model. In its most extreme case, it can be 1. However, usually it is not. It doesn't have its actual maximum at 1 level. And here again, the important message is that the value scoring itself seems quite well and seems quite well for training and test data. All right, so this is the first example for the regression task. And I would say let's make a quick pause here and then come back for the classification tasks. See you in the next video.